Hey everybody. So like a lot of people, I saw and watched recently the Ilya interview that came out today and literally like a few hours ago. And it was a great interview for me overall. I agree like 90%, not that it really matters, right? But I agree with like 90% overall of what Ilya goes over in this interview. And I agree, like I have a departure from Ilya, and very specifically in this interview, as well as like pretty much every other like prominent researcher, not every other one, but like a lot of the prominent researchers in this area, in that I am not convinced that we are facing an architectural problem, right? Like to me, I think that framing the problem, the wall, as Ilya puts it, is like a throwing out the baby with the bathwater if we frame it as an architectural problem overall. And so to me, I have a very like strong argument to me overall as to like my overarching argument as to why I think that it's important to say that it all boils down to architecture, right? So the problem is that as Ilya points out very specifically in this interview, that the models like just don't generalize, basically, right? Like that they compare to human generalization, like it's not even close, not even a contest. Like there's like you can't even call what the models do generalization. They have incredible interpolation skills and awful extrapolation skills, and that holds even with the models now and the models today. And then so the models now and models today are surpassing human IQ levels on standardized IQ tests. Like for example, like Gemini 3.0 is scoring like a 130 on the IQ test, but it is still like lags behind a human teenager or child when it comes to like extrapolation, right? And then like that is the big question overall that is faced with these models. And then the big thing that researchers point to within that is that extrapolation problem within this is an architectural problem, that it has to be an architectural problem. But to me, I don't like my silver bullet against that. Why I think it's not an architectural problem is because these models can be trained to the point where they do have Gemini, right, has an IQ of a measured IQ of 130, which means that on a variety of human benchmarks, a variety of tasks, it's able to like outperform humans on that task, essentially, right? So the answer is inside of the model, basically. It's just that the model can't extrapolate that answer, can't bring that answer outside of its training data set whatsoever, right? And that's like the big problem. And then so like everyone says like, well, it's like that has to be architectural. But if it's possible for every single answer to be within the model, then it's possible for the model to generalize to every single answer. And then like to me, that's the hypothesis. And then if you disagree with that hypothesis, then it's on you to present the evidence as to why that hypothesis is not true, right? Because you're saying that there is something that is within the models that would have to change within that equation. I'm just saying that like we just don't know, like if the answer is within the model, if it's generalizable, if we could train a model to be the best engineer possible, then it's 100% possible to train a model to generalize to be an engineer. We just aren't doing it right. And then like what would be the barrier or the gap within that that exists for that not to be true? And then again, like the impetus wouldn't be on me within that to prove that, because I can already prove that we can train a model to be an engineer, basically. And then so why can't we just like, what is the missing link between that and ability for it to generalize into an engineer? And then to me, it's like a very simple simple concept at this point, which it just boils down very specifically to geometry. And I'm going to outline and showcase this again to you and utilizing another example, right? And then so this is harping on this topic again repeatedly for a while now, but like this is to me like the most important and simplistic breakthrough that is needed to be understood within AI, right? Every single other person on the planet is framing this as an architectural problem that we need to, like, transformers are the problem, that we need to move past transformers, etc., right? I'm saying, like, no, it's like none of those are the problem. The problem is like how we're training the models, and then how we're training the models is in a fundamentally backwards concept that has been fundamentally backwards since the beginning of time, basically. And that concept to me, and it makes intuitive sense once you understand it and you break it down onto that level, right? So my argument is very specifically and very simplistically that as humans, when the nature of communication that we have established to communicate between one human and another is symbol based, right? Like it 100% relies on symbols, and that's been proven and known, because the question within it becomes, are those symbols necessary for learning, right? And that becomes the fundamental question within it. And then the fact that we are having to fundamentally bring that as the question, to me, is the problem within this, right? Because to me, the answer at this point is absolutely 100% that yes, learning comes fundamentally before the symbols, and then the symbols are inherently lossy in and of themselves, right? And then so by breaking down communication overall into essentially a lossy form of symbolic reasoning and symbolic structuring, we are in essence giving the model the wrong geometry to learn from a real world perspective from jump. Essentially, we are stripping the temporal element or the time-based element out of that geometry from jump, and then expecting that the model will somehow still be able to learn based off of that concept. And let me just like dive deeper directly into that concept, right? It's a hard concept to grasp and to understand. So to me, overall, we're reaching a fundamental wall within AI. And Ilya, I think in his interview, does a great job of pointing this out, right? Despite the billions of dollars poured into scaling laws, our models remain brilliant at interpolation, which is filling in the gaps between things that they've already seen before, but they're surprisingly terrible at extrapolation, predicting what happens next in a situation they haven't encountered. If you show an AI 1,000 pictures of a ball falling, it can generate a new picture of a ball falling. But if you show it a ball floating in zero gravity for the first time, it will likely hallucinate a floor. It fails because it's memorized the statistics of pixels rather than the laws of physics. When faced within this wall, the common refrain is that we need new architectures or symbolic reasoning models. We act as if the current engines are broken. Transformers won't work, none of it'll work. But the problem is not the engine. The problem is the geometry that we use to train the engine. The wall is surmountable, and it's far easier to climb than people think. We don't need to invent a new digital brain. We simply need to stop training our current brains on the wrong type of geometry. The core misconception: architecture versus training. The debate in AI often centers on architecture, the structure of the model itself. Critics argue that transformers, the architecture behind ChatGPT and other models, all LM models, are inherently incapable of reasoning. This is throwing the baby out with the bathwater. The engine is fine. A neural network is a universal function approximator. It has the capacity to learn anything, including the laws of physics. The failure lies in how we train it. Currently, we train AI on a Euclidean view of the world. We feed it static snapshots, tokens, images, and we ask it to minimize the distance between these. It becomes superhuman at drawing a shape that connects these static points. But reality isn't a shape. Reality is a flow. If you memorize the shape of a racetrack utilizing Euclidean or static math, you'll crash the moment that you're placed on a new track. But if you learn the physics of driving utilizing temporal and dynamic geometry, then you can drive on any track, even if you've never seen one before. And that's like how humans learn to drive, right? Like this right here is exactly like why a teenager can learn to drive in 10 hours, and then why we've now thrown a bajillion hours of learning to drive in AI, and it can't do it in a bajillion hours what a teenager can do in 10, right? And then so the hypothesis is that we don't need to rebuild the engine. We just need to shift our training objective. If we stop training AI to predict where points are, meaning the position, and we start training it to predict how points move, meaning the velocity and the vector fields, then extrapolation will emerge naturally from that. Within that, I conduct a simple experiment here to showcase this for you in real time, and I call it the spiral of time. So to prove that the wall is just a training artifact, we set up a toy universe governed by a simple physical law, a damped spiral. A particle starts at the outside and then spirals inward towards the center over time. And then we compared two approaches using these same fundamental deep learning tools. First one is the approach that anyone would use, right? This the standard Euclidean learner, standard MLP process, which is trained on static snapshots. It takes time as input and it tries to predict the position, the XY axis, and this represents the current paradigm of curve fitting, that it's all just this standard graph, right? XY graphs. And then the second method that we utilize is the temporal learner, or neural ODE, which is very extensively being researched within neural networks right now, which is trained very specifically on motion. And then so it takes those same positions, x, y, and it tries to predict the vector field. So instead of predicting x, y, it's predicting dx divided by dt, and it learns the rules of the change. And then so we showed that both models, the past, we showed both of the models the past, and then we hid the future, and then the results are that it was immediate and striking. So I'll showcase the results here for you overall, but essentially it learned, and it's a clear difference. And then so what we showcase within those results is a hidden geometry. I'll go through here and run through the experiment here for you, right? So this is the neural ODE extrapolation. And then so this is the first time just utilizing the experiment, utilizing temporal geometry, right? And so I wanted to see if the hypothesis would be true overall. So we generate the spiral, and then we generate the training loop on the spiral, and then we extrapolate the model. And then so essentially the model is shown the outside, right? It's shown like all of the purple stuff, the blue stuff, and then the red stuff is what the model is like having to guess towards, essentially what it has to learn, right? And then in this instance, it learns a perfect spiral exactly as expected, right? And then so let's compare that to Euclidean geometry, because so this utilizes a very different geometry than Euclidean geometry. And then so Euclidean geometry in this instance is what we're looking at in green here. So if you were to take a standard MLP model, like your standard neural network, and you train it on this same spiral, like this nothing changes within this except for the model, right? One is utilizing temporal geometry, one is utilizing Euclidean geometry. So one is your standard neural network that you would find in every single other instance, and then one is one that is taking very specifically time into consideration within as a concept within the data here itself, and then that's the one that is producing the spiral, whereas the classic Euclidean geometry is the green curvature that we see here that doesn't and can't reproduce the spiral, right? It can't fit this spiral. And then so when we go back here, essentially the green line, the standard model green dashed line memorized the training data perfectly. But the moment that the training data ended, it hit the wall that Ilya talks about in his interview very extensively here. It drifted off into space because it didn't know why it was spiraling. It only knew where it was supposed to be at specific times. It learned the map and not the territory. And then the black lines, so the temporal model glided perfectly into the unknown future. Despite never seeing the center of the spiral, it predicted it perfectly. Why? Because it didn't memorize the path. It learned the arrows around the path. It learned this, right? This, what we're looking at here on the right hand side, is exactly what the geometry that the temporal model learned that the Euclidean model can't learn, because there's nothing with, if you're just taking snapshots of this like a camera, this geometry never appears. And then so the model, like, there's literally impossible for a Euclidean model to see this. And then so the plot on the right reveals what the temporal learner actually saw. It didn't see a sequence of points, it saw a vector field, the purple arrows. And then these arrows represent the causal laws of the universe. Crucially, the model inferred these rules for the entire space, even the white void where no data existed. The Euclidean training asks, where is the data? The temporal training asks, what acts upon this data? This is so this concept is very important to understand. Like, this is the crux of this whole entire concept to me, and the crux of the problem. And I'm gonna frame it in as like simplistic way as I can, which in my own head and my own universe is like a SimCity type of world and SimCity type of universe, right? And so essentially what this is saying is that like that SimCity world, there's in the SimCity world, I use this analogy a lot. You'll have like rivers and tourists and things like that will come from off of the map, right? And then like there's this SimCity universe that exists, and then there's this universe that is not part of the universe. It just exists, right? It's just where stuff comes from. And then what is that universe? I don't know. What are the properties of that universe? I don't know. It's all defined like at its core by the CPU, which exists outside of the game, right? And then so utilizing that and the structure of that overall, the problem is that so when you're asking the model to interpolate, you're asking it everything about SimCity universe. Tell me what is happening within the SimCity universe, and the model is able to do that like very well, right? And then when the model has to extrapolate, you say, okay, what is happening in the universe outside of SimCity universe? Like, what's happening? Take a guess at what is happening at the river before it hits the SimCity universe. And then in these instances, and in the current instance, the model like is never trained on, like, the model doesn't even know that there is a reality that exists that is outside of the SimCity universe. It does, like, it's never even trained that this concept even exists. And then that's the approach of the question when you're asking it to extrapolate. You're asking it to extrapolate from something that it's literally never been trained on. And then to me, that's Euclidean training. And then so that's the difference here between Euclidean and temporal in this instance. And so, but to me, it's all a problem of training within that. The wall is thin. So this experiment suggests that the reasoning wall in AI is an illusion caused by our own training methods. We're currently taking continuous reality, chopping it into discrete static snapshots or tokens, and then stripping away the causal velocity. We're just literally throwing out time entirely. And then we hand this lobotomized data set to a supercomputer, and then we wonder why it can't understand cause and effect. And then the solution is easier than we think. We don't need to engineer consciousness or solve the symbol grounding problem from scratch. We just need to stop feeding our engines stills and start feeding them motion. We need to train them on temporal geometry. The engine is ready. We just need to teach it to look at the arrows and not the dots. Bottom line to me is that, like, we essentially just need to train the models on non-Euclidean geometry, on the fact that geometry and calculus from their inception have been broken with regards towards human concepts, and that they don't work right in a universe where everything is in motion. And then once you understand, you accept that, and then you give that as the baseline for the model and for its universe, it solves for all of these problems within the training itself. And then so the reverse of this is also true then too, right? Meaning that all of these like searches and quests for this like some sort of mystic alternative architecture that's going to solve these problems is not going to be very successful as well, right? Because they're looking in the wrong place. They're looking for the needle in the haystack in the wrong part of the haystack, where it's very simple. Like the problem is just like it's like right there, right at the surface of the haystack. If you just look at the surface of the haystack overall, and then so to me, I think this is a great interview overall. I think that these are important discussions, and this topic is a very like narrowly threaded topic, right? Like I hate this topic overall because it's like people are so quick to jump on anything that anyone says around this topic, period, right? And I think a lot of people are going to jump on Ilya's framing of the wall within this, right? And he outlines it very specifically within this, right? But like I think that the wall exists. He's very accurate with his framing of the wall. The wall is not insurmountable. I disagree with most people in that the wall is. I don't think the wall is an architectural problem. I think the wall is purely a training problem, as you can see here. I agree with everyone else, including Ilya, within this, that the problem is that we don't know exactly how and why the models work, and then so that's the problem that it boils down into. But to me, if you just incorporate temporal geometry as opposed to Euclidean geometry within this, and you frame it, models all of a sudden start working exactly how I would expect them to, as opposed to how exactly they are within the current status quo. And so to me, it all lines up. All makes sense overall if you just accept like the original sin of geometry, kind of as it were, and then realize that you need to actually include time within your geometry, which answers a lot more questions for you overall with regards towards physics, etc., things like that, right? Is time a stack on dimension with regards towards physics? Well, I mean, it's in every single real-world experiment that I'm running here. If you want to accept this as real world, the answer is no. It's 100% definitively not an add-on dimension, and it changes the math quite significantly when you do that overall, which is like why it's been a question. Which of these maths is accurate? The one that produces this green line, or the one that produces the line that you actually want it to? And then so in this instance, the math that's more accurate is the one that's lining up with your real-world expectations more, which is like that's how every single experiment has been proven before. And then so in this instance, the math that is lining up with the real world expectations is the black line, which is temporal geometry and non-Euclidean. And then so I mean, here it is. I can't lay it out any more simplistically than this. I'll leave a link to the interview here, as well as the article, and this from there you can access the collab notebook. And if you like this type of content, please like and subscribe. Thank you much.